Hi, my name is Amanda Bauer, and I'll be presenting Debiasing Bias Measurement. This is joint work with Kristian and Yunfeng Zhang, both excellent colleagues at Twitter. The key question we want to answer is, given a machine learning model, how can we accurately measure demographic group-wise disparities in model performance? This matters because inaccurate measurements can either overstate disparities, leading to unnecessary mitigation, or understate disparities, which can leave groups at risk for harm. A lot of the discourse in the algorithmic fairness literature centers around group-wise model disparities, typically referred to as bias. Suppose we have a machine learning system, like a gender classifier, a base performance metric, like the error rate, and for the people affected by the system, suppose we split them into different demographic groups, like their skin color. Then we ask, are there disparities in the base performance metric among the demographic groups for the system? In this example, with two groups, darker and lighter skin, the answer is clearly yes. There are disparities in the error rate for the gender classification system. In the example we just looked at, the disparity was immediately obvious. However, what happens when we consider several groups at one time, which is typical for any real-world setting? This table is taken from the excellent work in the Gender Shades paper, where the authors illuminated massive disparities for gender classification systems. They consider many models, base performance metrics, and demographic groups. While this information is undoubtedly useful and necessary to look at once you have a model that you're ready to deploy, answering questions like what is the degree of group-wise disparities based on information in this table, or how do models compare to one another with respect to these disparities, quickly is very difficult. Machine learning practitioners that are doing model selection and trying to pick one model out of hundreds or thousands based on hyperparameter choices need to answer these questions quickly because they need to understand the trade-off between model performance and group-wise disparities. Most of the work in the algorithmic fairness literature only deal with two or a few groups where disparities are immediately obvious. However, there is some work and some tooling that tries to answer the previous two questions when dealing with many groups. They look at things like how the best and worst group compare to one another by looking at the difference between the maximum base performance metric and the minimum. It also looks at things like the variance to understand the variability in the base performance metric. In both of these examples, the closer these numbers are to zero, the less group-wise disparities there are. We've identified these types of metrics and called them meta-metrics because they summarize what is happening for each of the groups in the base performance metric. For example, we take all this information in the table and distill it into a couple of numbers that we can now use to answer those two questions. Unfortunately, naive estimates of metametrics are statistically biased upwards from the truth. This matters because we'll end up with inaccurate measurements, and it happens because some subgroups have a small sample size, especially intersectional groups. Our main contribution is to more accurately measure the variance metametric with our double-corrected variance estimator that takes into account these small sample size groups as well as variance picked up during bootstrapping when obtaining confidence intervals. You can end up with different conclusions about disparities depending on whether you use our estimator or the naive estimate. Please see our longer talk for more information. The key takeaway is obtaining accurate measurements of disparities is non-trivial. Despite these challenges, we have proposed a solution to more accurately measure these disparities through our double-corrected variance estimator.